Hey guys, welcome back. I'm going to go over the study guide for charge, electric force, and electric field calculations, drawing electric fields, solving for acceleration for our test. All right, so where we started out was Coulomb's law, which is going to be the attraction or repulsion from any two charges. And this is given by the equation that the force between them, which we call F with the subscript of E, is equal to a constant times the charge magnitude of one of the charges times the charge magnitude of the other charge divided by the distance between their centers squared. So it's an inverse square relationship, just like gravity is. So the constant, which I would always give you, is 9 times 10 to the 9th newtons meters squared over Coulomb squared. And then I have two protons. They're going to have an elemental charge of 1.6 times 10 to the negative 19. And keep in mind that we simplified this. It's really 1.602 times 10 to the negative 19. And dividing by the distance between them, which is a reasonable distance because we know that an atom's width on average is about 10 to the negative 10 meters. So I'm going to put this in a calculator just to make sure that the answer key is correct. And it's important that you guys practice actually putting this in the calculator. There are a lot of exponents, and then in addition on the test, it's hard for us to know what a reasonable answer is. And I did get the same thing. I got 1.36 times 10 to the negative 8. It's a force, so it's going to be newtons. And since they're both protons, that tells me that they're repulsive. So we don't put the signs into the equation. We use the signs to decide the direction of the force. Number 2, find the electric force between a cloud of 6 electrons and a cloud of 4 protons if they are separated by 4.8 times 10 to the negative 4. Is the force attractive or repulsive? So this is going to be attractive because we have a cloud of electrons and a cloud of protons. So a cloud of something that's negative and a cloud of something that's positive. So again, same formula. This would be on the board. One of two new formulas in this. Electric field one will be the other one. So I have K, Q1, Q2. Our K is going to be the same. Our K is going to be 9 times 10 to the 9th Newton meter squared over Coulomb squared. And now I have 6 electrons. So that's going to be 6 times our charge magnitude E, which I'd also put on the board for you guys, which is going to be 1.6 times 10 to the negative 19. So it's going to be 6, 1.6 times 10 to the negative 19, and 4, there's 4 protons, 1.6 times 10 to the negative 19, and I'm going to divide this by 4.8 times 10 to the negative 4th meters, and then this gets squared because it's an inverse square relationship. All right, plugging this in my calculator, let's make sure that we have the correct answer on the answer sheet. And I got 2.4 times 10 to the negative 20. And I said it was attractive. So we're not going to put the sign in these. All right, we can have elemental charges, which would be protons or neutrons, which are protons or electrons, or we can also have objects that have an amount of charge on them. And very often it's a quark, because that would be an insulator, or a pith ball, because that would be an insulator, and the charge on there will just stay. A small quark with an excess of 6 microcoulombs, so micro is 10 to the negative 6, is placed 1.1 meters from another quark, which carries a charge of negative 5.3 microcoulombs. What's the magnitude of force between the quarks? Is it attractive or repulsive? How many excess electrons are on the negative quark? How many electrons has the positive quark lost? So we're going to solve for what the force is, decide if it's attractive or repulsive, and then we're going to decide how much electrons the negative one gain and how many electrons the positive one lost. So it's always going to be the electrons that are traveling with us. So I'm going to have 6 times 10 to the negative 6. So our prefix micro says that it's a million. And then I'm not going to put the negative in here because I'm looking for magnitude. So it's just going to be 5.3 times 10 to the negative 6. And then this is going to be divided by 0.1, and we have to make sure that we square it. So I got 28.62. So that agrees with what the answer key says. And then since one is negative and the other is positive, they attract. All right, so how many extra electrons? So the whole idea is that these electrons are what makes up the charge, whether we're losing electrons or gaining electrons. And all of our charge is made up of an amount of these. So the least amount of charge we can have is 1, and then we can have 2. So you can't have a half of an electron, you can't have a half of a proton charge. And that's what it means when something is quantized. So there's the smallest amount of charge you can have, and energy as well as quantized. We'll see. So I'm going to plug this in. And I got 3.3125 times 10 to the negative 13. So this agrees with what how many extra electrons a negative one has. I'm going to do the same thing to find out how many electrons the positive one lost. So that's going to be the 6 times 10 to the negative 6. Again, 1 elemental charge is 1.6 times 10 to the negative 19. And I got 3.75 times 10 to the 13th, which that agrees with what our answer key says. All right, so electric field. So this was made up by Faraday to try to explain how one charged thing could affect another charged thing over a distance. This action at a distance that I explained to you guys was very hard for people to understand back then in the 1800s, 1700s, and earlier. So this formula is very close to what the force one is, and electric field is big E, and this is just going to be KQ over R squared for a point charge. Again, our K is going to be the same, 9 times 10 to the 9th. We're not going to put in the sign of our charge, because this is going to give us the magnitude. Again, the sign will give us the direction, right? The direction is given by what a positive test charge would feel. So a positive test charge is going to be attracted to a negative charge and repelled from a positive charge. Very much like the electric field hockey lab you guys did. And again, we still have the inverse square relationship. Again, I'm going to put this in the calculator just to make sure that it is correct. On the key, because I don't remember. You would think if there was error, I would have corrected it, but sometimes I am not as reliable. And so we have 5.51. The units for this is newtons per coulomb, and it's going to be towards, because if this is a negative charge, a positive test charge would feel a force that would pull it towards it. And again, this is arbitrary. We'll see when we get into capacitors how they decided what was positive and negative. Ben Franklin's responsible for that. It has to do with accounting, as silly as that might seem. All right, find the electric field 1 meter from a proton. So a single charge can have an electric field, and it's just saying what that field is at some point away from it. So, again, we have K cubed over R squared. I have 9 times 10 to the 9th Newton meter squared Coulomb squared. The charge of a proton is this elemental charge, 1.6 times 10 to the negative 19. And we're 1 meter away. So I'm expecting a small field. So I got 1.44 times 10 to the negative 9. Newtons per coulomb. And again, if we're saying that we have a proton that is positive, it would want to push this away. So the field is going to be going away from the proton. All right, so these field lines, you guys need to be able to identify the sign of the individual charges and also the relative strength of the two charges. So in this one, I have Q2 and Q1. Q2 has arrows going away from it. So that tells me that it is a positive charge. So a positive charge would repel a positive test charge. Q1 has field lines going towards it. That would tell me that it is negative. A negative charge would attract a positive test charge. And again, these are arbitrary, but we saw these field lines in the video. You can actually see them, and you probably saw them as well in the FET. All right, so if the charge magnitude sign ignored of Q1 is 2, maybe that's 24 coulombs. I'm guessing that it is. It got cut off. What is the charge magnitude of Q2? All right, so we have to see how many field lines are going away from Q1. It's got to be 2, right? The first problem with this thing. So let's see. So Q1 has 6 field lines that go towards it. Q2 has the same 6 going away from it. But it has an additional 12 going away. So it must be 2. This 4 is like, cross that out. So if Q1 has a charge of 2, Q2 must have a charge of 6 because it has 3 times as many field lines, so it should have 3 times as much field. All right, uniform electric fields, where the electric field is the same everywhere, which is actually what's going on inside of a capacitor and inside of a cathode ray tube or an electron. So an electron, a proton, and a neutron are each placed in a uniform electric field of 2 newtons per coulomb directed to the right. What is the magnitude and the direction of the force exerted on each particle? So field lines go away from positive and go towards negative. Our force is equal to the electric field times the charge. So my electron is negative. It's going to be repelled from this side and attracted to that side. So it's going to go to the left. My proton is positive. It's going to be repelled from this side and attracted to that side. It's going to go to the right. My neutron has no charge, and it's going to feel no force. And again, of those elementary particles, neutron's the last one that was discovered. It wasn't discovered until the 1930s by Chadwick. All right, so our force for both of these is going to be the same because they have the same charge magnitude and the same field. So this is going to be 2 newtons per coulomb times 1.6 times 10 to the negative 19. Again, I'm not putting the sign in. The sign's just telling me the direction, and I already determined that. So for each one of them, they're going to feel a force that's 3.2 times 10 to the negative 19. As I put a 2 down instead of a 3. And then since there is no charge on the neutron, it just has 0. So there's no direction associated with that. Calculate how long it would take the electron to travel 4 meters. So they're going to have the same force, but they're going to have different accelerations. So I know that the acceleration is related to the second law. So my acceleration is going to be F net over M. So this is going to be my 3.2 times 10 to the negative 19 coulombs, and this is going to be the mass of an electron, which I would give you. So an electron is a lot more easy to accelerate because it's 1,800 times less massive than a proton. All right, so once I solve for my acceleration, I have 3.5 times 10 to the 11th meters per second squared. I also know that my initial velocity is 0, and it's going 4 meters. So going back to kinematics, I can cancel out that because my initial velocity is 0. So I'm going to multiply by 2, divide by the acceleration, and square root. And we have to be careful with these elementary particle problems because there's a limit to what you can do with Newtonian mechanics and kinematics equations. If we get too fast, if we get more than 1% of the speed of light, which is 3 times 10 to the 8th, So if you're getting in the order of times 10 to the 6th of what your velocity is, we have a different set of equations. So I got 4.78 times 10 to the negative 6 seconds. On the answer key, I got 4.77, but it might have been how I rounded the acceleration. All right, so we're not going to do potential energy or work in this section. We're going to include that when we do potential energy and work in the other one. We do have a couple conceptual questions on here besides the charged ones. So 2 initially uncharged conductors, 1 and 2, are mounted on insulating stands and are in contact as shown above. A negatively charged rod is brought near but does not touch them. With the rod held in place, conductor 2 is moved to the right by pushing its stand so that the conductors are separated. Which of the following is now true of conductor 2? So since these are conductors, the charge can move freely. And so what's going to happen is polarization. So each one of them has the same amount of positive and negative charges to start with. But this negative charge is going to cause negative ones to be pushed away. When those negative ones are pushed away, it's going to leave positive ones. So when I separate them, I'll make it a little bit bigger. So I can see the video is not showing up. The negative ones that go away leave positive ones on number 1 and push negative ones onto number 2. So it's true that conductor 2 is negatively charged and also lost its stand. All right, guys, so good luck on the test.